Let's take a look at aerospace materials. So make sure to add this to your engineering notebook. These are some of the commonly used aerospace materials, and we're going to take a look at them sort of from beginning to end here. So here's some factors for selecting materials. There's function, what's it going to be used for. Then there's some properties. So one is strength to weight ratio. Here's a carpenter's pencil, a little wood pencil. And it's strong and it's relatively light. Then you look at stiffness. A wooden pencil is quite stiff. There's very little flex, very little bend to this. Toughness, it's relatively tough. You can dent it fairly easily. There's also resistance to corrosion. Now wood will start to break down over time, so that's not one of the properties that wood has. Fatigue and effects of environmental heating. Wood's not so great with environmental heating. And then you have production. Is it machinable? Well, wood isn't, but you can harvest it, and then you can form it and shape it as you want to. So one thing that I do want to talk about when you go back to stiffness, it's very stiff, and since it doesn't give, that might be a good thing, but if you apply too much pressure, it will just break outright. So it's also very brittle. So we'll talk about that in a bit. So and then production, how available and consistent is the material going to be? If you have some crazy alloys, it's really difficult to make. So here's some stresses that materials need to overcome. Your average commercial aircraft has a 30-year life cycle. It operates for 60,000 hours. This is a commercial aircraft. It's about 20,000 flights, and 100,000 miles of taxiing, which is 4 times around the Earth's circumference. So some interesting facts for you. So this is a total average maintenance and service cost is usually double the original purchase price, just to keep it maintained. Some flight stresses that it has to overcome are some pressure differential to the fuselage and outside. We took a look at pressure differentials anywhere from 0 kilopascal to 60 kilopascal. Temperature differentials, ground temperature, which is whatever it is on ground surface that you're at. If you're at the equator, it might be really hot, or if you're flying up to Alaska, it may actually be minus 56 Celsius. It's definitely possible. And then you've seen the temperature lapse rate, where it can get really, really cold as you are flying at high altitudes. And then there's impact of landing. The landing gear has to support the aircraft. The wings have to flex. When it lands, the wings flex up, so there's a lot of stresses right on the joint from where the wing attaches to the fuselage. There's also downward force of their own weight. And then the tires are going to accelerate from 0 to about 400 kilometers per hour instantly, which is that little puff of smoke. So they have to be able to handle that. So you want to keep in mind that reducing material density reduces airframe weight and improves performance, which means that you'll have better fuel efficiency, climb rate, G-force loading. As long as your weight goes down, then you have less requirements for lift. Material density reductions are 3 to 5 times more effective than increasing tensile strength, modulus, or impact resistance. So rather than making your airplane super, super strong, it actually is more efficient and more effective to make it less dense. It's 3 to 5 times more effective. So some early aircraft, now we're going to start looking at materials, were just built out of wood, and they used spruce. It was widely available. It was relatively uniform from piece to piece, so you didn't have drastic changes in density from one wing to the next, which some of us saw with our balsa gliders. As the density of the wood changed, one side of the aircraft was a little bit heavier. It has a relatively good strength to weight ratio, and again, there's different properties depending on the different directions. So if you look at the directions of the wood, if you load it on end grain, it's going to have very different properties than on edge grain or face grain here. And it's relatively easy to repair, so it seems like the miracle material. However, it is very sensitive to moisture, rot, and insect damage. And it's a natural product that is lower consistency than a man-made product. So a solid, consistent metal is going to be consistent all the way through, whereas wood is just not going to be. So it's rarely used today because of those things. Some people use them for home-built aircraft because it's cheap and readily available material. And then just a neat little fun fact, the Chinese selected oak for the heat shield of a re-entry vehicle because oak has a really, really high flame point. So here's some different material forms. You may have a sheet material, so something you might want to add. A sheet is less than 1/4 inch, and this is typically for the skin of the fuselage, wings, surfaces. So you have sheet metal usually in these rolls here. And you might also have plates, and plates are greater than 1/4 inch, and these are usually machined into various different parts. So you can see this one has been milled out, and that's like plate metal, usually a lot thicker. You also may forge it, where it's just plastically formed by compressive forces. You're pushing it into shape using different types of metals. And then there's also extrusion, and we've seen all these videos in the robotics class where the material is forced through the dies and it creates a cross section. So if it is, and metals themselves, solid metals themselves, can be solidly extruded with enough pressure. Then there's casting. You melt it down, you pour it into a die or some sort of mold. Now we're looking at specific materials. So one of them is aluminum alloy, and this is sort of cutting edge in the 1920s. It is the most abundant metal, so to be able to use aluminum is really important, and in fact to the point that truck manufacturers are starting to build trucks out of aluminum because they can make them a lot lighter and they're really strong, so that improves fuel efficiency. Pure aluminum is relatively soft, so they have, through lots of materials testing, realized they needed to make it an alloy, which means mixing different kinds of metals. So again, it's relatively or readily formed. It's at a moderate cost, and there's good resistance to chemical corrosion and very, very good strength to weight ratio. So strength and stiffness are affected by the form of it. If it's a sheet, a plate, bar, extruded, if it's forged, and heat treating and tempering can help affect some of these things too. Stronger aluminum is typically more brittle, and again, that just means that it won't deflect very much until it actually fails and snaps altogether. So here's a couple different alloys. There's actually 9 double of them, and you can see that they're labeled just by these numbers. So if it's a 1000 series, it's 99% pure aluminum. If it's a 2000 series, it has copper in it. Here's an example of that. The most common alloy is 2024, and it has 4.4% copper. That's the most common secondary element besides aluminum. So these different series will show you what type of aluminum alloy that it is. Some really high strength applications are in the 7000 series, and that's using zinc, magnesium, and copper. And if sheet metal aluminum is clad with a thin layer of pure aluminum for corrosion protection, zinc is also used as a corrosion protection. Aluminum lithium, this has the same weight savings as composites, but it can also be formed using standard techniques, so another good alloy. Steel, moving on, is very cheap and easy to fabricate, and it's first utilized in fuselage construction. The steel tubing replaced those the wooden wire brace constructions, and now today they use it as high strength and fatigue resistance. It's for wing attachments, anything where you need something that's extremely strong. Steel alloys would be with iron and carbon. So carbon is going to add strength to your soft iron, but it also adds brittleness. So typical steel alloys have 1% carbon. And some other common alloys include chromium, molybdenum, nickel, cobalt. These are just different alloys that may be mixed in with it. Steel is influenced by heat treating and tempering, so you can change its brittleness, its ductility. So some of them can have moderate strength and good ductility, or high strength and they're very, very brittle. They don't flex at all. So you may want a product that gives, that flexes before it breaks, just given what the conditions that it's going to be in. And then materials temperature is raised from 14 to 1600 degrees Fahrenheit, and that's the point where carbon goes into a solid solution with the iron. So you really have to get it hot to make that alloy. Then moving on to titanium, it has an even greater strength to weight ratio and stiffness than aluminum, and it can sustain extremely high temperatures like that of steel. So that was kind of steel's benefit. Now titanium gives you a little bit of both. But the downside is it's difficult to form. It has really high forming temperatures and stresses. So if you want to extrude it or form it or shape it, you got to get really hot and you have to have a lot of pressure involved. It's also very, very expensive, which is why it's only used in only applications that need this super great strength to weight ratio and to be able to sustain high temperatures like that of steel. So moving on, that's why it's extensively used in jet engine components, that extremely high temperature and really a lot of pressure in there. Also in lower airspeed aircraft, it's for high stress airframe. And it's also used in landing gear beams because that's a part that is undergoing a lot of stress. You don't want that to fail. So the way that they actually form this is they use this superplastic forming or diffusion bonding, and they take extreme pressure and temperature and press it together, and in doing so it sort of melts or fuses them together, so there actually is no seam when the two pieces are together. It's completely indistinguishable, and that's it's saying down here. You can't tell where the joint is when you do diffusion bonding. So if you're curious about it, Google it. It's kind of a cool bonding process. Magnesium, another material, has good strength to weight ratio. It tolerates high temperatures, but if you get too high, then it is flammable, which we'll talk about in a second. It's easily formed by casting, forging, or machining, so it's used for engine mounts, wheels, hinges, brackets. Engine mounts is kind of an interesting thing. Where the engine's really hot, wouldn't there be an issue of it exploding? Well, so since it is prone to corrosion, it has to have protective finish, so a lot of times it will be coated on the outside, maybe zinc coated, so that it doesn't just catch on fire. That is usually bad on an aircraft. So you don't want to put it in an area that is difficult to inspect, so you might miss that some of the protective finish has eroded away, because then your plane is going to blow up. Really high temperature nickel alloys, here's a few of them, and these are great for hypersonic aircraft that are getting extremely fast, so they have a lot of drag, and they get really hot through the atmosphere. And this one, Haste alloy, is primarily used in these engine parts. So again, some of these are heavier than aluminum or titanium, difficult to form, but they're really great at heat resistance. So now let's look at some composites. Composites are using two different materials together, where each one separately might not be very strong, but together they're extremely strong. And first used in the 60s and 70s, part of the empennage, this back part here, of the F-14 and 15, and used of an epoxy and then some type of material. So again, horizontal stabilizers, rudders, fins. Since the mid-1970s, they started using carbon fibers, and we're going to actually make a carbon fiber composite with an epoxy and some styrofoam later on in the course. So in the 80s, composites were expanded from 2% to 27% on the Harrier jet. They started using them a lot. Now modern fighters have 20% composite material because it's really light, so they're saving 15 to 25% on weight, and that just makes it a lot more efficient. The 787 uses about 50% composite and even has composite wings and fuselage. So they're using different materials in here to really reduce the weight but still make it really strong. Our last material is ceramic, and ceramic is phenomenal for high temperature resistance, which makes it great for tiles on the space shuttle for re-entry. So again, they're also used for engine exhaust nozzles because they're really never going to ignite or break apart at the temperatures that engine exhaust is used at. And then for space shuttle re-entry, they can easily withstand that heat from space shuttle re-entry. One interesting fact about that is, since they're so good at withstanding this heat, it's also difficult to find a way to adhere them to the surface of the shuttle. So that was actually a really interesting engineering problem that they had to come up with, was how do you get these ceramic tiles to stick, because the adhesive would then melt off even when the ceramic protected it. So if you're curious about that, that's a great Google question. And that's it.